Hi, my name is Becky Irwin from North Carolina State University and the Rocky Mountain Biological Lab. And I want to give a shout out to Melanie Kalsnell, also from NC State, and the Sevieta LTER, who provided some very nice slides for today's talk. And so as we're considering strategizing and prioritizing places to monitor for native bees across the US, one of the things that we might want to consider doing is tapping into existing infrastructure. And one of the types of infrastructure that I'm going to talk about today are biological field stations. And I think the take-home message that you can get from this talk is that working at field stations provides some unique opportunities, and in particular, the opportunity to use contextual data to try and understand how bee population numbers are changing over time and why. And so what I'll share with you today are three topics. So first, what and where are some of these biological field stations located? What are some of the things that they provide for a potential monitoring program? And then two case studies. And so here are some examples of networks of sites and stations across the US. And so the common theme across all of these, if you were going to collectively look at them, we have a variety of biological field stations in urban and non-urban sites, and agricultural and non-agricultural sites, and across a diversity of different habitats already. At many of these stations, there are institutionalized data that are collected, so common ways that data are collected across the sites. And in many cases as well, there are independent ways that data are collected. And then even if we drill down to the state level, there are state level agricultural research stations that also within a state provide a diversity of different habitat types and commodities alongside which bees could be monitored. And so the top five here are sites that are funded by various funding schemes. We also have our federal sites that we learned about in the federal partnership meetings, such as the National Wildlife Refuge System. And so just to drill in on one of these, NEON, the National Ecological Observatory Network. So this is a network of 81 sites. Those 81 sites are spanned across 20 different ecoregions that have been designed or identified in the US. And of those 81 sites, 47 of them are terrestrial. And so NEON's designed to collect long-term open access ecological data to better understand how the US ecosystems are changing. And so the data that are collected are open access. It includes a broad range of airborne sampling schemes, as well as abundance and phenology of certain types of organisms and their parasites. In the vast majority of cases on the prior slide that I showed, all of those sites and networks of sites, bees are not monitored at them. And so it provides a unique opportunity to think about how we could use field stations as a way to monitor native bees. So what do some of these field stations provide? I think it's important to keep in mind that each field station is unique in terms of what they provide. And so it's really important to have a good conversation with the science director at a field station before you decide to work there. But here are some examples of types of things that could be provided. And I think the two number one things that could be provided are potentially open access data sources. So trying to understand why bee populations are changing over time. So having access to that additional contextual data, as well as physical infrastructure. Many field stations have well-resolved natural history collections of which bees might be a part of them. And there may be access to historic bee data at some of these sites. As I mentioned, field sites provide access for physical infrastructure for you and your team, so somewhere to stay. There may be help with permitting and field site access. Some provide help with the actual data collection, although this is more rare. One of the benefits of working at field sites is there is a community of scientists there working on a variety of topics. And so again, it may give you access to contextual data to understand why bee population numbers are changing the way they are. And then for sites that are set up in networks across the US, there is the potential for national comparisons across sites. And so again, to summarize those opportunities of working at field stations, access to contextual data, physical infrastructure, well-resolved collections, and a network of scientists working together. Some of the challenges, and I think probably the number one challenge would be expense. So it's important to keep in mind what the expense structure is at a field station. And if you're thinking about doing long-term monitoring, how those expenses will increase over time. There could be overlapping research interests. There could be issues with some field sites not allowing insect collection if you want to do lethal collecting. and there could be issues with access to specific sites. So again, it's important to keep in mind that field stations provide both opportunities and challenges to work at. So let's look at two quick case studies. So the first case study comes from the Sevietta LTER. So these are our long-term ecological research sites, of which there are 28 spread across the US. The Sevietta is located in central New Mexico, and so it's one of their desert ecosystem sites. And so the Sevietta monitors across 8 different habitat types, trying to understand how climate change might modify state transitions among these different habitat types. And a bee monitoring program was set up in 2002 by Karen Wright using a funnel trap-based system, and it collects approximately 340 species annually. So along with this bee monitoring, there are a variety of other types of data that are institutionally collected by the LTER at Sevietta, of which there's meteorological data, plant data, data from other types of organisms and the bees as well, and they are all publicly available. So for example, this allowed Melanie the opportunity to combine the long-term bee monitoring data with some of the meteorological data to understand drivers of bee phenology or bee abundance. And so on the y-axis, we have maximum yearly abundance, and using a simple aridity index, which combines temperature and precipitation, she was able to explain about 71% of the species, their abundances annually. And then we can compare that across taxa. So that same aridity index is also very important in understanding annual net plant primary production. And so the point there is a researcher could take the bee data that are being collected and combine that with other types of data sources to try and understand variation in bee abundance. Now let's look at a completely different field station. So this is the Rocky Mountain Biological Lab. It is not an LTER site or part of any of the other networks of sites. Instead, it's an individual or independent field station. And so individual researchers can apply to work here. And so in this case, the data are collected by individual researchers, but there's been great opportunities for those researchers to collaborate. So for example, the weather data that I'll talk about, or environmental data, are collected by an individual, Billy Barr, who started collecting data in the 1970s, and all of his data are publicly available. And he's also the business manager of RMBL. At the same time period in the mid-1970s, David Inouye started recording flowering phenology in set plots. That's now been taken over by a team that includes Brian Inouye and Nora Underwood. And then finally, David encouraged me in the late 2000s to start monitoring bees at the RMBL. And so I can take advantage of David's wonderful flowering phenology data and Billy's environmental data to try and understand drivers of bee population fluctuations over time. And so just very briefly, the RMBL bee data, we use the standard bee plot protocol that includes pan traps and netting every 2 weeks throughout the bee flight season. We've been sampling since 2009 in 17 sites, and all of our data are available on the Open Science Framework, both David's flowering data and then the bee data as well, using a simple data request form. So for example, we've been able to combine across these individual data sets, so Billy's environmental data, David's flowering data, to try and understand bee abundance over time. This was an analysis that Jane Ogilvie did, and so she wanted to understand whether these climate drivers had direct effects on bee abundance or indirect effects mediated through floral resources. And what she found in her case is that the indirect effects via floral resources were much more important than any sort of direct effects of precipitation and snowmelt date on bee abundance. So that's one example of combining across data sources. A second example is we've been able to compare phenological responses of organisms from a diversity of different taxa. And so this is a project that's been spearheaded by Rebecca Prather, who's a postdoc on the project. And so she was very interested in comparing plants, insects, mammals, amphibians, and birds. And so researchers provided their data, and she's been able to do a comparison across taxa to show that at least for some environmental variables, such as snowmelt day of the year and mean spring temperature, all of these organisms show fairly similar phenological responses. And again, bees are part of that insect response. So again, it provides an opportunity to compare across taxa. So in terms of tapping into existing infrastructure, There are networks of field stations and sites across the US that provide pretty good spatial coverage and a diversity of different habitats. Working at those field stations can provide contextual data and physical infrastructure for bee monitoring programs. It's important to keep in mind both the opportunities and challenges of working at field stations. And our case studies reveal that there are opportunities to combine across data sets to understand drivers of bee population responses and to make comparisons across taxa. Thank you.